Okay, so welcome to the afternoon session, and we have Ziyang Gao, and he'll tell us about the generic positivity of the Beilinson-Bloch.
Thank you. So today I'll talk about the generic positivity of Beilinson-Bloch height. It's a program that recently initiated with Shouwu Zhang, and up to now we have obtained some results about the simplest cycles, the Gross-Schoen cycle and the Ceresa cycles. So you may see the title of on this website to be the heights of the Gross-Schoen and Ceresa cycles, and we hope to initiate this program and in someday extend the results to other cycles. But today, let me start with some motivation, and this is a motivation more in algebraic geometry, or some, for example, the second part also in some number theory like Kudla program. So let the x be a projective variety, and then let's take an integer, a negative integer. And here are two questions that one can ask almost immediately. Let's say, is there a way to detect whether a cycle class is torsion or not in the child group? So whether it's torsion or not rational equivalence. And is there a perfect pairing on the child group? Not torsion, of course. Is there a perfect pairing? One tool that can help to answer these questions is the heights. It's a very common tool in arithmetic geometry, and I'm going to explain what I really mean. So first of all, let's start with the basic definition of heights. It was introduced by Weil in 1928. It was used to measure the size of rational points, rational numbers, or algebraic numbers, just like absolute value to measure the size of integers. For rational numbers, it's indeed just the maximum of the absolute value of the numerator and the denominator, and then we take the log of that. This is for rational numbers, and we can generalize this definition to algebraic numbers. For any number field K, we can define the height of a point on the projective space. The K points on that. But for a general number field, because the class number is not necessarily 1, so we may not be able to write down in a unique way as a ratio of two integers. So we do this sum. We sum over all the places of the log max of the v-added absolute values. So this is well defined. You can check it using the product formula. And we do this normalization. We divide it by the degree of the number field so that it will not depend on the choice of the number field that we choose. Like you can do the computation in K or in any finite generation, a finite extension of K. So this function is then well defined over Pn of Q bar, all the algebraic points on Pn, and this is what we call logarithmic weight height. And there are two important properties of this height, and they are not hard to prove, but they are very important. First of all, is this height has a lower bound, and it's even a non-negative. It's bounded from below by 0. That's because in this definition, you can always choose one of the coordinates to be 1. You can divide things so that one of the coordinates is 1. So this is always non-negative. And second is the Northcott property. That's we have only finite many points, algebraic points with bounded height and bounded degree. This is the Northcott property. And again, this is not hard to prove, but many different finiteness results can be reduced to this one or use this one to prove. And in this particular case, we also have a very nice characterization of all the height 0 points. They are exactly the points where the coordinates can be chosen to be either 0 or roots of unity. So this is the weight height on Pn. And if we have such a function on the projective space, then we can also define it on any projective variety or even quasi-projective variety. You simply choose any embedding of x into Pn using any very ample line bundle and so on, and then compose it with the weight height that we defined before, so that we get a function from xq bar to r. Well, this function depends on many things, like it depends on the embeddings. So it depends on the line bundle we choose, and depends on the global sections that we choose. So they are not well defined, but they are well defined up to a bounded function. So we can still talk about this this is called the naive height, even though it is not a well-defined function, but it is well-defined up to a bounded one, the bounded one. So we can still talk about the boundedness from below. Has a lower bound, even though this lower bound is not that well defined in general, but there is a lower bound. And for Northcott property, simply it is the same statement. And these are also easy to prove once you have this definition, because it's the composition of some embedding with this logarithm weight height that we defined before. But here, we can only talk about bounded from below, but there's nothing like height 0 points and so on. That's not well defined. Still, in some cases, we do want to talk about this actual function, this genuine function, and I'll give 2 examples of that on the next page. But before that, let's make things a bit more abstract. Let's talk about any quasi-projective variety defined over a number field, and let's take any function on the set of algebraic points to the set of real numbers. And we will call H a dominant height, or sometimes called weight height, if it has a lower bound and satisfies the Northcott property. Okay. Just these 2 important things. And here, again, I'm just talking about the lower bound. And in some situations, we want this lower bound to be more precise. And here are the 2 famous examples I want to talk about. The first one is on abelian varieties. On abelian varieties, we do have a polarized dynamical system. You can choose a symmetric ample line bundle, and we have the multiplication map, like say multiplication by 2, and then the pullback of the line bundle and the symmetric ample line bundle is just 4 times this line bundle. So somehow we have this polarized dynamical system, and if we have that, then we can choose a nice height function defined by this line bundle by some take limit process. So we have a genuine function. This is really a function from a q bar to r, and it satisfies these 2 properties. And better, it is a genuine function. The lower bound is 0, and it vanishes precisely on the torsion points. So this behaves very much like this logarithmic weight height we defined from the beginning. So that that height also vanishes precisely on the torsion, but to GM, something like that. And if you have this one, then we can see that we do have a perfect pairing on AK mod torsion. Because of this, this defines a positive definite quadratic form. It defines a positive definite quadratic form on AK. But here, pay attention, I'm really talking about AK mod torsion. But for this case, it's even stronger. You can base change to R. Okay, and this example is useful. This height is very useful in studying many questions on arithmetic, on abelian varieties. For example, this height kind of was used to prove the model weight theorem for high-dimensional abelian varieties. Even though not exactly this height, but the height this one being a quadratic form is somehow implicitly used, and it's also used in some formulation of Birchman-Schmidt-Dye conjecture and Gross-Schoen conjecture, Gross-Schoen formula. You see this height for some Heckner points and so on. Another example is appeared first of all in Follins's proof of the Model conjecture. He defined the height of an abelian variety, but in my talk I'll only talk about curves. So curves of the Jacobian of curves. It is associated to each curve we attach a number which is called nowadays the Follins's height of the Jacobian. So the Follins's height of the abelian variety, and this defines a function on the modular space of curves. So for each curve defined over Q bar, we can associate the number, and this is we call it a Follins's height or stable Follins's height. And this was used to prove the Model conjecture. Okay, so these are 2 examples of dominant height functions. By the way, proving that this height is a dominant height is one big part of the proof of Model conjecture. Okay. Now these are functions on points. They are evaluated on points. And we want to study cycles. So first of all, we want to extend these things to cycles. And there's the general theory of Gillet-Soulet, but I'm going to talk about a more precise version. That's the Beilinson-Bloch height. These are genuine functions. So in the 80s, they proposed a series of conjectures Now this is called the Beilinson-Bloch conjecture. They try to extend the height from points to higher cycles. But there's one condition: these cycles should be homologically trivial. So the cycle class, the image under the cycle class map is 0. That's because we want to extend things to a family of homologically trivial things and to do the arithmetic intersection and so on. This was only conjecturally defined. But in some cases, they are unconditionally defined, like these two cycles, the Gross-Schoen cycles I'm going to talk about, or any cycle in abelian varieties, which are homologically trivial, and the product of curve with the surface by Shouwu Zhang. And they conjecture the positivity of their height. They conjecture that this height is also always non-negative and is 0 precisely when the cycle is torsion in the child group. So if this was true, then we will have a perfect pairing, And very few results is known for this Beilinson-Bloch height. There are some family that you know that these heights are all 0. For example, hyperelliptic curves, this height is always 0 because we can use involution of the Ceresa cycle. I'm going to talk about that a bit later on. And they conjecture the finiteness of the rank of the child group and formulated a generalization of the PSD conjecture. So again, there are some cases with very few results are known. And it can be shown that if C is torsion in the child group, then the height, if it's well defined, then it's 0. This is, but we also conjecture the other direction. Okay, now let me focus on the cycles that we're going to talk about today, this Gross-Schoen and Ceresa cycles. They are defined in different ways, first of all. Secondly, their arithmetic behavior and geometric behavior are kind of similar. It's just that sometimes one prefers this Gross-Schoen cycle, especially in number theory. Sometimes people prefer Ceresa cycles, especially in algebraic geometry. Let me define what they are. So the starting point is we want to have a smooth projective curve, irreducible and so on, defined over Q bar, defined over C, and the genus is at least 2. And then we take a point which is the canonical divisor divided by 2G minus 2. We want to use this point as the base point for the Weil-Jacobi embedding later on. Now, the Gross-Schoen cycle is a 1 cycle on CQ. And Ceresa cycle is a 1 cycle on the Jacobian. They are defined as follows. So the left-hand side, this is for the Gross-Schoen cycle. We have CQ, which is these 3 directions here. C, this is like the origin of the 3 directions. And we have all the diagonals, like this black one. This is the actual diagonal in the 3 directions. And we also have the partial diagonals, like this orange one, this purple one, and this blue one. They are the diagonals in 2 variables, in 2 directions. We fix one of them. And then you also have the diagonals in 1 direction. And we do the alternating sum up to here. So this is a 1 cycle, and we call it the modified diagonal. One can check that this is indeed homologically trivial. So this is the Gross-Schoen cycle. The Ceresa cycle is defined on the Jacobian. So we use the Weil-Jacobi embedding based at C. And so here, this curve, this red curve is C, and this blue curve is pullback by multiplication by -1. And the Ceresa cycle is the difference of them. So saying that the Ceresa cycle is torsion or trivial means that we can deform this red curve to the blue curve rationally over time. This is what it means. Okay, so these 2 cycles, a priori, they are very different. They even lie on different spaces. Why do I say that they're similar? Well, first of all, they will be simultaneously torsion, and secondly, their height will be proportional. I'm going to write it down later on, but here, let me, first of all, say the goal of our project. We do want to propose a systematic way to study the positivity of the Beilinson-Bloch height. And the starting point is, as many of these functions, we use this height to define a function on a suitable parametrizing space and study things on the parametrizing space. And for these 2 cycles, we do have a modular space of curves, which is a nice thing. Okay, now we can define these two functions. I call them the Gross-Schoen height function and the Ceresa function. So it sends each curve to the Beilinson-Bloch height of the corresponding cycles. The first one is the Gross-Schoen cycle, and the second one is the Ceresa cycle. Okay, first, both of them vanish on the hyperelliptic locus, and secondly, actually, this cycle is torsion in the Chao group if and only this cycle is torsion in the Chao group. And third, their heights are proportional. Maybe not really 6, but it's some it's some number depending on G. But anyways, one is 0 if and only if the other one is 0. And you want to study the positivity, it's enough to study whichever one you prefer. And then for the positivity question, we can divide it into different grades. Like first of all, is this function a dominant height on the whole MG? Meaning that does it have a lower bound and satisfy the Northcott property? The answer is no, because both of them vanish on the hyperelliptic locus. So there can be no Northcott property on this part. So the best we can expect is it is true on a Zariski open dense subset. This is the best that we can expect. And of course, if this is true, we expect to define over Q. Well, the height is somehow you can apply the Galois group, but still you will see why I emphasize this defined over Q. And if this is true, then it sort of gives some sort of generic positivity that we want. And this is the generic positivity that I will talk about later. And secondly, can we really write down what this locus is? Well, first of all, this locus should not intersect with hyperelliptic locus, but are they all? And if not, can we really write down this locus explicitly in the sense that given any curve, can we directly detect whether it's in the locus or not? That would be very nice. And third is this lower bound non-negative. And what can we say about the height 0 points? If we can answer all these questions, then we're basically done. And of course, we should assume G at least 3, because otherwise every curve is hyperelliptic. When G equals 2, every curve is hyperelliptic, then we know everything. Okay. So
is the Zariski dense open set like a function of your proof, or should it be false outside of that?
It should be false outside that.
It should be false. Okay.
It should be false. Yes. Okay. Actually, this is our theorem. I write it in a slightly strange way. So assume G is at least 3, we define the maximal Q-bar Zariski dense open subset on which this Gross-Schoen height is a dominant height. Okay, the maximum one, this exists by some Noetherian properties and so on. First of all, saying then the question 1 is equivalent to say that this ample locus is not empty. And it's defined over Q, then defined over Q. And we also give a partial answer for part 2. It can be constructed, but it's not explicit. In the sense that unfortunately, given any curve, we're not able to tell whether it's in this or outside of this or not. But there is some construction, and you will see that it's really in this construction that we emphasize here. Still, so we do have an answer for part 1, and we have a partial answer for part 2. And we need to, of course, express this more explicitly and then show the lower bound is the negatives. These are at least the things that needs to be done, even for these 2 cycles. And there are some more I will talk about in the last slides. But already from part 1, we can say, well, it satisfies the Northcott property on this. Then if we set, okay, so how about the points of height at most 0, They are bounded heights, and if we fix the number field, the degree is also bounded, so there are at most finitely many of them. So this follows directly from the Northcott property already that for any number field, there are at most finitely many curves lying in this ample locus. These curves are defined over K such that the height is negative. At least, of course, fixing a number field is less a problem in this because usually when people study cycles, it's okay to talk about cycles over a number field. But this finitely many, we don't expect to have any of them. There shouldn't. So this is the thing. But still, we have this generic positivity here. Okay. And now let me talk about this proof. First of all, I want to underline some key points in the proof. There are some arithmetic parts and the geometric parts. The arithmetic part, the first tool we use is this the theory of eidetic line bundle developed by Ziyang Gao in 2021. It's published this year. And in the proof, we also use Morse inequality, some very serious analytic tools. The upshot is we want to show that this height function, it is a height function defined by some line bundle. And then we convert the problem to the geometry of line bundle. And we do want to prove some vagueness, to compute the volume of this line bundle to prove it to be positive. For that, we need to use this Morse inequality I'm going to talk about later. And there's a geometric part that we study the Betti map, the Betti strata, and Betti form. The main tools we use, first of all, we use O-minimality for period maps. This is really what allows to transfer many results and techniques for Shimura varieties to general Hodge theory. So yeah, this is very, very important. This is by a serious work of Baker, Green, Webb, Klinger, and Zimmerman. And in this case, we also need to use some superversion of X-Channel, this functional transcendence results. For this case, we use the result of Chu and independent proof by Klinger and myself. Yeah. So these are the key ingredients, and the link between them are works of Griffiths and works of Hain, our Canadian local heights. Okay. So let me start with this eidetic line bundle. I won't really give the definition of eidetic line bundle, but just a very rough idea of what it is. So this theorem or proposition, whatever it is called, we say that there is an eidetic line bundle such that the Gross-Schoen height is exactly the height defined by this line bundle. And an eidetic line bundle, what it is a matrix line bundle, meaning that so we do not only study study MG. The MG is a variety defined over Q, but we really study the integral model of MG over Z. And at each place, Archimedean place, we put a metric. Then we use complex geometry to study these things. And at finite places, we also need to do something, especially at those bad reduction places. We also put some metrics at every place. So these things are called matrix line bundle. So even though I'm talking about eidetic line bundle over MG, I'm really talking about things over integral models, The key point here is these matrix line bundles, they should be approximated by Hermitian line bundles. This is a very nice theory on integral models of compactifications of MG. So we consider really all the compactifications of MG and all the integral models of them. And then we consider all the Hermitian line bundles and do some limit many times. And there are some things called models, some things that are Cauchy sequences and so on. But in general, this is the idea. We can put metrics, but we don't want some arbitrary line bundles. We really want those to be approximated by these nice ones, so that we can have a theory to talk about the volume, like arithmetic Hilbert-Samuel, all these kind of things. Okay, so these are eidetic line bundles that we want to study. So pay attention, they really actually live on integral models. And these are the L bars I'm talking about. Okay, and for this theorem, there are several constructions. So Yuan gave a construction of this one, and in my paper with Shouwu, we also gave another construction, and this is our construction. The key point is we use very seriously this power dynamical system on the universal Jacobi. So we use somehow the abelian scheme structure. This is this is one of the obstacles that we are confined to Gross-Schoen or Ceresa cycles. We at least already in this construction step, we are confined to that because we need to use this one. So we start with the Poincare line bundle on the Jacobian or the self product of the Jacobian. So this is the Poincare line bundle. When we write on the Poincare line bundle like this, we see immediately that this part, the first part is ample, but the second and third part, they are also ample. We're doing some differences, subtractions of this ample thing by also two ample things. So for example, we don't know whether this bundle is NEF or not. We don't know whether this bundle is NEF or not. This is actually one of the biggest problem in the hardest point in our proof. We don't know the NEFness of this. Whatever like geometric fiber or just arithmetic things, we don't know whether it's NEF or not. But we do have a line bundle like this, the Poincare line bundle, and we have this power dynamical system, so we can extend this line bundle to an adelic one, and we can put it back to CG across CG, and then we use the link parent to push to MG. So the two things I want to emphasize is, first of all, we really need this power dynamical system so that we're confined to Gross-Schoen and Ceresa cycles. And secondly, we don't know whether this bundle is NEF or not. We think they are, but we don't have a proof yet. We don't have a proof yet.
Over AG, is it not NEF?
No.
Okay.
No. This one. Yeah, because you subtract these two. We really don't know.
Can you what, sorry?
Subtract these two. Like if you restrict to the diagonal, it's fine, but otherwise you don't know. Yeah. And for this theory of adelic line bundle, there's also the so-called generic fiber. Remember, I said that this L bar is really actually defined over integral models. So we can also define things over the generic fiber of the integral model. But even for that, we are actually doing some limits. We're considering all the line bundles, all the compactifications, and doing some limits. And they are approximated by line bundles on the compactifications. So even over Q, there's a new theory there. I will always use L tilde to denote this generic fiber. This is more like a geometric situation. Like if MG were compact, were projective, then we are doing nothing here. But MG is not. So even on the generic fiber, there's a new theory to study. Okay, so this is our starting point. We need to have something geometric to define our height. And then what we want to do, we want to study this line model. We turn this arithmetic question to a more geometric one. And then part one for this dominant height thing, it is equivalent to this generic fiber is a big line model. That means up to some power, it has a global section, and then outside the divisor of this global section, we will have a lower bound on the height and so on. So this is part one, and then we want to descend to Q in a very nice way. And for this one, we need to characterize all the subvarieties such that this line bundle restricted to that has volume zero. Of course, I haven't really say what is the volume, but it's going to be on the next slides. So up to now, I want to do a very quick summary. We want to use adelic line bundle because there's a nice theory behind it. We can define the volume, the global sections, and it behaves well under height theory. Okay, now let's see. We want to study this volume. We prove this formula for the volume. First of all, what is volume? Well, it is exactly like in algebraic geometry because we're talking about this generic fiber. And in algebraic geometry, the volume is some limit of the dimension of the global sections of powers of n, or powers of that line bundle, normalized by divided by n factorial and dimension to the power of n and so on. So that's still the definition in this case. It's just at the boundary, we need to put some condition. So these are like well-behaved global sections which increase like grows moderately at the boundary and so on. So the left-hand side, we do have these global sections. And this formula, in that case, it looks very much like something that we know in algebraic geometry, that the volume, if the bundle is NEF, well, first of all, we note that the volume is generally computed as the self-intersection, the top self-intersection of the line bundle. And secondly, when the line bundle is NEF, then this top self-intersection equals this integral the curvature, the top wedge power of the curvature. So we're proving the same thing in this new situation, but there are several difficulties. First of all, we need to adapt everything to non-projective case. So this new theory here, it is known that this volume, it's still the top self-intersection. That is fine. This is still the top self-intersection, but we don't know whether this line model is net or not. We don't know. So we cannot apply things like Hilbert-Samuel to link the top self-intersection with this integral. And in our paper, we proved this directly without using top self-intersection. We proved this directly. So we really wrote down that this volume where we're doing some H0 and we sort of want to compute things and approximate things using, let's say, bound H0 and handle this H1 and so hard cohomology and so on. And this is where we use the nice Morse inequality. So we use our construction of this eidetic line bundle. We do have this approximation that we have, and the volume will also approximate, will also converge to that. And we use the Morse inequality to bound the H0, to compute the H0 on even open things. On even open things, we at all the models, And something I'm not going to be precise is we again need this explicit in construction to get fast enough convergence. This step is also confined to Gross-Schoen cycles because of this last sentence. We still need the abelian varieties to do some average on torsion points, so to get a fast enough convergence. In general, you can always get a weak convergence, but here we really need a strong one to get actual formula. So somehow this is like one of the hardest steps of our proof to prove this volume identity. Okay, so this is the arithmetic part. Now let's summarize a little bit. So this is our goal. We want to show that this dominant height, this is the dominant height on the Zariski open dense subset defined over Q bar. That's equivalent, almost equivalent to say that the volume is positive. And we now prove this volume identity. And we apply that to mg, S equals mg. Then what do we want? Well, from this identity, we see that if we can prove the following three things, we're done. The first is this curvature form is always semi-positive. It's nowhere negative. Secondly, if we take the top wedge power of the whole mg, it is not identically zero. It is not identically zero. Then this volume on the whole mg will be positive. And to descend things over Q, we need to study where this vanishes. And we sort of want to show that it vanishes always on Zariski closed subset. And here I put a quotation mark, we will see why later on. If we can prove these three things, and then plus this volume identity, then we're done. So now we are boiled down to these three things. And that goes into the geometric part with a bridge over here. And this bridge is, so we show that this curvature form equals the Betti form, which I'm gonna explain later. But actually this was already proved by Robinson-Young before the language of that line bundle were available and before Betti form was probably brought into attention of the story. Okay, so from this one, then we can replace this curvature form by the Betti form later on. And then we will study the geometric part, prove the algebraicity of the Betti strata, that's part 3, and the criterion for the non-vanishing of the Betti form. I should say that in the first steps, everything really is confined to Gross-Schoen and Ceresa cycles, almost everything. But here in this step, we can apply it to any reasonable family.
If you show that the curvature is semi-positive, wouldn't it show its net? Or
no, the definition is different. No, the definition is
The metric is defined only on the open part, right?
yeah.
So you need to control
we need to control the boundary and so on.
I see.
Yeah.
But on the other hand, for the Zariski closeness, this subset looks like the O-minimality. augmented base locus of your line.
Maybe.
But then it would give the dice.
Maybe we can talk later. Okay. So let me then turn to the geometry. How much time? Oh, 2 minutes. So I'll do this setup in a more general situation that's any family. So we will take a family of projective varieties over C. So S is quasi-projective. It could be MG, for example, in our case. And X is a family of projective varieties like CQ or the Jacobian. CQ or the Jacobian. And we'll also take a family of homologically trivial cycles or codimension N. Like in the first case, we're taking the family of Gross-Schoen cycles and codimension is 2. And in the second case, we're taking the family of Ceresa cycles and the codimension is G minus 1. It's G minus 1. And we're going to use this intermediate Jacobian to study this. For any point on the base, we define the so-called intermediate Jacobian as follows. As a real torus, it's very simple. It's just the 2n minus 1 cohomology, the real coefficient mod the z coefficient. So it's a real vector space mod a lattice. It is just a real torus, which is compact real torus. On this real coefficient cohomology, we can also give a complex structure. That's we do the complex cohomology and then mod the middle degree filtration, Hodge filtration. Then this is a complex torus, which is compact. Okay, this real torus, it doesn't depend on the choice of S. It has fixed dimension, so it's the same real torus. The real structure is the same. But as the S varies on the base, the complex torus, the complex structure varies. The complex structures really vary. And Griffiths constructed the Abel-Jacobi map from the child group homologically trivial cycles to the intermediate Jacobian. Very similar to how on curves. So on curve, you have a point, but any point on the curve, after you choose a base point, it can be thought of as that point minus that base point. So it is also a degree 0 cycle, which is homologically trivial, and then mapped to the Jacobian. Yeah, in that case, also the intermediate Jacobian is exactly the Jacobian. But in general, this compact complex torus doesn't have an algebraic structure. So this makes certain things much more complicated sense. Now we are going to do a family version of this. The correct way to write it down is to do this relative cohomology, and then we do the family version of this compact torus versus real torus. It becomes this one. So the left-hand side, I'm writing down as a family of compact complex tori. The right-hand side is just a local system of real tori. It's the local system. And because we have this Green-Fisk morphism, so here for each small s, we have a homologically trivial cycle, which is the fiber of Z. It can be mapped to the right-hand side. So that's like we have a section here. We have a global section here from the base to this family of tori. So it maps each point S on the base to the Abel-Jacobi image of this homologically trivial cycle. Okay. And then we have two ways to see this. First of all, let's take the differential of this, so the tangent map at each point of this homomorphic section. And the tangent of this family of complex tori, if we forget about the complex structure, it's just this real one, but then it's a local system, so it's almost something trivial. It's like a product. So it can be decomposed into these two parts, the horizontal part and the vertical part, and map it down to the vertical part. This is called the local Betti map. On the other hand, we have a system of real tori, so this defines a foliation. It's every leaf is the constant leaf for this real thing. And then we put it back here, then it's a foliation. The nice thing about this foliation is that every leaf is still holomorphic. every leaf is still holomorphic. And now we have to finally can define what is the so-called Betti form. It is the pullback of the polarization. It is the pullback of the polarization on this real thing, H2n minus 1 XSR. Yeah, this is the, sorry. This is a two-form. The pullback is a two-form. It depends on the choice of the polarization. Here is something I didn't really say too much about the polarization, how it's chosen and so on, but there is a polarization which is a pairing, which is a pairing here. It's not symmetric or anti-symmetric, it's alternating, something like that. The thing is, if we talk about this one on the, well, it can be put back to the tangent space of S. It can also be pulled back to the tangent space here. If we pull it back to the tangent space of the whole intermediate Jacobian, relative intermediate Jacobian, then we have some alternating sum. We may have some alternating sum of positive things, negative things, negative things, and so on. So we have no control of this form. But if we put it back further to S, this S is algebraic, is basically the only algebraic thing in the story in general. Still, we get something semi-positive. This is by Greenfield's transversality. Greenfield's transversality tells us that this map, the tangent of this map, the image is contained in some small part of the horizontal, Greenfield's horizontal direction. It's something very small. It's the whole thing if and only if this family is an abelian scheme. This family is an abelian scheme. So in this sense, somehow it's very different. The abelian scheme situation is very different from other variations because, yeah. On the other hand, we can define the so-called Betti strata. This will be somehow the vanishing locus, almost the vanishing locus. This is defined to be all the points such that this leaf, the image of this section intersect with the leaf non-trivially, non-discretely. There is at least a curve. Because all the leaves are holomorphic, so this is something complex. This is something complex. Okay? So this is the Betti strata that we define. And here on the left-hand side, we have this one-one form, which is proved to be semi-positive. This is the so-called Betti form. On the right-hand side, we have, let's look at this one-one form taken to the top wedge power. When is it zero? Well, if it's everywhere zero, then on a very large part, this mu s must intersect with the leaf non-trivially. If it's everywhere discrete, then it will not be zero. It will not be identically zero. So somehow this is identically zero if and only if this is the whole thing. Well, this is not really very precise because you may have sometimes you may have some points where it is tangent, but it doesn't contain any positive part of the leaf. But it cannot happen globally. So that's why I put a quotation mark here. This is almost equivalent. There may be some subtlety in general. But still, that's fine. And what we're going to prove to be Zariski closed is actually this Betti strata. It captures also the global picture somewhere. And this is what we prove. We prove that the Betti strata is Zariski closed, and we prove a criterion for it to be the whole thing. So it's a criterion for this Betti form to the top wedge power to be zero. And again, we use O-minimality for period map to use definable Chow. And also this Greenfield's conjecture, saying that the period map factors through an algebraic map, it helps a lot with simplifying the proof. So all these are important, especially this O-minimality. It's very essential in this application. And mixed X-channel actually used twice in this proof. The first one is really just X-channel itself to translate the problem to some highlighting section property. And the second time, we want to use something called geometry over pink. This itself is an application of X-channel. It has a rather long story. First of all, in the Shimura world, it was proved by Yumo, and this kind of statement was proved by Dao Ren and myself in some Shimura cases. And then later on, under Klingler's formalization, Bagvik, Klingler, and Yumo proved it for variation of pure Hall structures. And the version we use is this ultimate version proved by Bagvik and Rubanik for variation of mixed Hall structures. Probably I should emphasize that these first proofs all follow from a preprint of Yumo, which uses O-minimality, so no effective results. But by the Urbanik's result, the proof is different. So they have some effectivity results of this geometry grouping. Okay. So then actually we will have this corollary of our theorem applied to the Gross-Schoen case. Then we have that this is semi-positive. This is actually Haynes' result. And second, this is not zero everywhere. And in this case, also there is another proof by Haynes. There's a proof by Haynes. He applied to the whole MG. And we also proved that this Betty strata is RC closed. This is now covered by Haynes. But I'm gonna say maybe something about this later on. But okay, now with this in hand, we're able to conclude our main theorem. Here are some questions that we do want to ask. Of course, there's the natural question: can this work for other families? I think I try to explain where it does and where it doesn't work. Basically, the identical line bound, the arithmetic part doesn't work now, but the geometric part works. But even for Ceresa cycles, for these two cycles, there are some questions which are interesting and to be answered. First of all, I think this is one of the biggest questions. Can we actually compute this one? In the proof before, because in the end we descend after all the descent and so on, what we've shown is this part two is this ample locus is the complement of the Betty strata. It's exactly the complement of the Betty strata. And we sort of prove that this Betty strata is defined over Q. That is why we need, that's what I really mean by descent over Q. But this still doesn't answer the question that given any curve, can you check whether it's in the Betty strata or not? This doesn't answer that question. And to answer this question, I think maybe Haynes' proof is more explicit, even though still up to, in his paper, he didn't really compute this Betty strata for any G, but his proof is really more explicit than ours for this purpose. And I think, in my opinion, there's more hope to read off what is this ample locus from Haynes' proof. Yeah. Second is, well, we do want to show that this L tilde is NF, or even more, L bar is NF. Well, L tilde being NF is probably more approachable as a question, because yeah, as Phil pointed out already, the C1 is semi-positive in the interior, but the boundary is another problem. Still, it's not an easy question, but this suggests that it's a lot more approachable. For this L bar, it's gonna be a bigger question, because if one can prove that the L bar is big, then this lower bound thing can be improved to be bounded below by zero. That will be much nicer. It will be much nicer. So the third part of the third question is basically corresponds to improving the lower bound to bounded below by zero. This is like the third question. And the last one is back to the torsionness of the cycles. Is it true that every point in this ample locus, the Ceresa cycle is non-torsion? It is true or not? Well, just by the method itself, it is true for all the transcendental points. But of course, the more interesting question is, how about the algebraic points? That we don't know, but we conjecture, we think that there's no point to be torsion in this locus. For this, there are Matt Kerr and Salim Tayo has some reason. They constructed another set where all the transcendental points are non-torsion. But I think the better way to really tackle this problem is really to look at this locus and try to prove that every point is non-torsion here. It's non-torsion here. I think with Wan Lin Li, we know that these torsion points are not analytically dense here, but already it's an interesting question to prove that these torsion points are not Zariski dense here. And from that, basically, I know how to deduce, if one can show that these torsion points are not Zariski dense in this locus, then I think one can show that none of the points is torsion. No, but still, that's very hard. And the main obstacle that I find now is that these fibers are, none of them is algebraic. That's the biggest issue. So I think that concludes my talk.
Questions?
You know curves which are not in MGM,
Yeah, hyperelliptic curves are not.
apart from these ones.
It's very, I know the Klein quartic is in that. There are some papers where they construct some families where the Ceresa cycle is identically torsion, then they will not be in MGM. Yeah, all these examples. Yeah, so I cannot write them down now, but yeah, people know.
Other questions? Okay. Oh, good.
So the it's like if you will consider the Hodge bundle over the modular smooth projective curves, then can we pull the, for example, the adelic line bundle to that Hodge bundle?
Yeah,
And then that's all those properties still hold? Or do you think?
I think that's some work of, so that Hodge bundle being adelic is proved in Yuan Zhang's book. Yeah, and that's more related to maybe this uniform model long conjecture thing that Yuan gave the second proof for curves. It's related to that, not this one, not this one. But that's more of a question of a family of abelian varieties. It's different. At least in my opinion, it's very different.
I guess I'm curious about this very first step. Like, you have this height, this Beilinson-Bloch height, which is some complicated, take some model, do some stuff.
Yeah.
And you reformulate it as the height of some line bundle on MG.
Yeah.
You sort of hid that from us. What goes into that? What goes into establishing that it shows up that way?
Yeah, we want to use the properties of these adelic line bonds. For example, we want to use the bigness property.
No, you want it. So on a priori, why is it clear that like the point by point height, the Beilinson-Bloch height of the cycle, corresponds to the height of some bundle in MG?
Yeah.
It is clear?
There was work by Shouwu Zhang in 2010 where he studied this Beilinson-Bloch height of Gross-Schoen cycles. At least it was hinted that there should be some bundle.
So what goes into that? Like, what are the ideas to show that?
Just he computed do the local computations and related to arithmetic intersections.
He just does local by local stuff.
Yeah, so arithmetic intersections. But at that time, the theory was not available, so the line model wasn't written.
I mean, is this some general thing where if I give you some family of cycles over a base, which locally will give you homologically trivial cycles, then the Beilinson-Bloch height gives you the height corresponding to some adelic line bundle?
We don't know. We want to show that. But we don't know.
Understood. But you hope that that's true?
Yeah.
Okay, gotcha.
It should be.
Yeah, so maybe can you explain a little bit more so how you show the Philly strata, right? So apparently they are only real analytic. So claim they are Zariski closed. So I think two ingredients, right? So they are definable, they are complex analytic. So can you roughly sketch how you get this?
No. Actually, if you can prove that they are complex analytic, it's basically done by definable Chow. They're automatically algebraic, but it's not shown in that way. The algebraicity is proved directly, but of course, definable Chow is still used, but it's not. First of all, show is complex analytic. It's not clear at all. Yeah, I think the questions are the same. The heart of the difficulty of the questions is the same.
Okay, if there are no more questions, let's